Good afternoon, statisticians. This is Dr. Schulman reaching out to you. I'm letting you know that we're doing chapter 9 today, and chapter 9 is all about t-tests, which is great because I just did t-tests in the last video because I wasn't sure if it was going to be in this. So I'm really happy we got a chance to do it. However, for this chapter, they're all bunched into one. So the way that they have it set up in the course is that independent samples, single sample, dependent sample or paired sample, right? Like, or two sample, like all these things are all in one. Like, we're not doing part by part by part. We're just doing one all together. So I'm going to try to explain the differences between the types of t-tests, but I'll do my best to make it clear for you. Okay. So I'm going to share my screen and then I'll do the review problems. So here we go. I'm sharing my screen. I am just going to start with some notes. So Intro to Statistics 9, and we have to do all these problems. But in order to do the problems, I have to show you what t-tests are. So basically, the most common, there's three common things of these t-tests, and they all kind of have similar names. And maybe I could type it. So we've got the one sample t-test, the independent sample t-test, because these are both like two sample t-tests. So like if you have two samples. And then we have this one that's like, we still have two samples for this one, but this dependent t-test. And thank you for all the emails of like telling me what's been working and what's not. And the dependent samples t-test, it's like you have one group, but they get tested twice. So let me try my best to explain the three differences. So if we have a t-test, they all work the same way. This is the most common way. The independent samples t-test to me is like the most common thing. And that's the t-test where it's just the mean of group one. We want to know how it relates to the mean of group two, or it's like the sample of group one. How does it relate to the sample of group two? That's all that means, right? But if we have a one sample t-test, like say if we want to do a t-test one sample, basically what we're doing, we are relating it to the population mean. That's all we're doing. We're just taking our data and we're relating it to some population mean. It's just like the proportions. It's almost exactly the same idea as we were doing for the proportions and the z-scores. That's all it really is. We're just using a different type of equation to do it. So that's the one sample t-test. Now the two sample t-test or the independent samples t-test, we have two separate groups. Usually it's men and women, young people, old people, however they want to break it down, two separate groups. We compare the means of the data. And this is the one that I did in the example in the last video. So you can watch that. I do it by hand and all that stuff. I'm going to do these by hand. I don't think so. Why? Because they don't show you any of the stuff. They're just expecting you to do them. So if you want to watch me do one of these by hand, just look at the previous video, okay? Okay, so the last one is also really important. So this dependent samples t-test, okay? Sometimes it's called independent samples. Now, when they're talking about dependent samples, we're still comparing means. All of these are always comparing means. We're still comparing means, but now it's mean one, like mean one, and then it's mean one later. So it's like a pre-test, post-test. That's X2, that's X1. I mean, we're comparing, this would be no hypothesis. We're comparing the same people. So in independent, we could have different sizes. Sometimes on dependent, we could have different sizes, but you usually throw out that data. Like you don't want to use the same data if they fell off in the middle of the experiment. So usually dependent samples always have to have the same exact sample size. for both groups because it's like a pre-test and a post-test, or like before an exam, after an exam, or it's like before treatment, after treatment, but it's the same people. So hopefully that was helpful. I have StatCrunch here just so you can see it. So StatCrunch, and this is like just before I jump into it. So StatCrunch, if we go to um, these are the three things we're going to use. If you go to proportion stats, like we said before, now we could do it with two samples. So it's just like we were doing for the proportion stats, but we could do this with two samples. Isn't that nice? So we have that option. We have two groups, so we can do a proportion. So that's right here. It's the same exact way we did it before. Now, if we have our t-test, there's one sample. So we need to be compared. And if you do like this, like with summary, notice that we have the sample standard deviation, right? We have to have this. We need all this stuff for the summary. Okay, now if we want to do the two sample with summary, now we need the mean standard deviation sample size for one group and a second group because we have two separate groups. And notice that the sample sizes can be different. For all of these, whenever you have this, in order to get the right answer, you have to pull the variance. It has to do with the formula. It just means that if we have like different sizes in groups, we should always be pooling that variance just to make sure it doesn't affect the results. Okay. I didn't want to go too crazy into it, but basically all of this stuff is, no matter what it is, okay? If we're doing a t-test or we're talking about two samples, like if we're doing a proportion, they don't give you all the information or all the data you have to do a proportion style. But I don't want to jump too far into it. So we're just going to do the problems. I'm going to use StatCrunch the whole time. And just let me know if you need help. Okay. So I'm going to do just about all of them for the chapter review. I might just do them all, but I really just want you to follow along and try to understand. Now, if anything is too tough, what should you do? Look at the last video. I do the formulas. These are without the formulas. So, but just know all we're trying to do is see if the means are different. The means most likely will be different, but can we prove to somebody they're different by using statistics to say we're 95% sure that this isn't due to chance? This mean is different from this mean. And that's all we're really doing. All right. So how do we get to it? We go to my math lab and mastering. We click open my math lab. This is gonna pop up. I clicked StatCrunch, so I have it here. And then I also have the e-text. I clicked it, so I have it right here. I tried to be prepared this time because I don't know. I'm trying to do better with the videos. Okay, so here are the questions. So let's get started. Hopefully this stuff is easy for you. So here's the review exercises. We have to do numbers 1 through 5. So here's number 1. The denomination effect. So we've got Priya Raghubir and Joydeep Srivastava from the Journal of Consumer Research. All right. Well, just like everything, I try not to trust anything. Well, that makes me sound like I'm crazy, but I always want to know where the stuff comes from. It says junior. So I'm gonna go to Scrimaggio, and you should be doing this every time you see an article, just to make sure it comes from a good source. So let's actually look up the Journal of what's it? Journal of Consumer Research. Okay, so here we go. The Journal of Consumer Research. We look at it. Notice that there's 3 of them. This one's a Journal of the Association. That's in the US, Family Consumer, but this is just Journal of Consumer Research. It's out of Oxford. Has everything about it. Been around for 50 years. It says exactly what it does. Very familiar to the psychology one. Its SJR ranking is actually really high. The documents are pretty flat. Way more citations. So this is getting more and more used, more and more popular. We just care about the Q score. You don't want to look at the small ones. It's a Q1. Nice. This means it's one of the best journals, which is really nice. So we got its information. So we can trust it. It's been very rigorously done. So here we go. Determine whether people have different spending characteristics, whether they have larger bills, a $20 bill instead of a $1 bill. So they're trying to say that if we have more, like a higher bill, we'll be less likely to spend it versus a $1 bill. So they did this dollar bill group. So they gave 46 people a buck, then they gave 43 people quarters, and they want us to test the claim using 0.05 with the data from the study. What do we have to do with this? Oh, we just have to just as review exercises. I'm not quite sure what we have to do. But I guess I'll just see, right? Let's just test it. So because they just give us the amount of people who spent the money and the subjects in the group, to me, I don't have like a mean, I don't have a standard deviation, so I can't, without a mean, I can't do a t-test. So this is telling me that I have to do a probability. So I got to do the probability. Uh, so basically, it's that crazy formula with the P and the Q, right? We're going to use the binomial piece. Usually we did this with one sample, but now we have two. So let's use StatCrunch to do it. So here's StatCrunch. I'll put on the side. So I'm going to go to stats, proportion stats. Not one sample, we got two. We don't have data, we just have the summary. So number of successes for the first one was 12 out of our N, which is the number of people. And for sample two, I have 27, and our N is what? 43. Okay. They don't say a confidence interval. We could do a confidence interval. It just says test that claim using a 0.05 significance level. Okay, we just have to test the claim. So if they wanted to test with a confidence interval, we'd be doing this. Is it more? The article concludes that money in large denominations is less likely to be spent. So what does that mean? If it's less likely to be spent, that means 2 should be bigger than 1. So 1 minus 2 is 0. So this is 1 and this is 2. So if I know that I want 2 to be bigger than 1, this should be negative. It should be less than 0. Because I want this number, we want 2 to be bigger. That's what we're testing. I want to be less than 1. That's why I have to have it as less than 0. And I could be wrong. It's number 1, so we can check it. I also want to show the critical value. They say at the 0.05. I click compute. Here we go. Sweet. Our statistic was negative 3.48, and our critical is negative 1.644. This is bigger than this, and also you can say that this is less than 0.05, the p-value. So either way we slice it, using the critical value here, the stat is bigger than the critical, or you can look here and say this is less than 0.05, but either way it's significant. So we got it. So we did the first one. I'll put in the information. So for number 1, our Z statistic is negative 3.487. Our Z critical, our critical value was negative 1.644, and our p-value is 0.0002. What does this mean on the chart? Well, if we're saying the critical is here at negative 1.644, because we just care about this bit, and our value fell here, our t-stat fell here, the negative 3.48, we could say what? Significant. We can reject the null and say what? We can say that people spend more quarters. We could reject the null and that says that people spend more quarters than dollars, or you can write whatever you want. Let me double check it in the book. All right. They say that the first one would be equal. Oh, they wanted these. So they wanted the null hypothesis, which we know the first one is equal to the second one. So there's an alternative hypothesis. We said that P1 was less than P2. Oh, well, sorry. They want it written this way. P1 minus P2 is less than 0, which is fine. Test statistic is correct. Z critical is correct. Reject the null. Nice. Then they wrote a sentence. You can write your own sentence, but that's the answer. Please write your sentence. All right, let's go to number 2. Hopefully that was clear. Let's see what 2 has in store for us. Construct the confidence interval that could be used to be tested in claim 1. What feature of the confidence interval will lead us to the same conclusion? Okay, so we get a harder question. So we want to be 5% sure, right? So 5% is our alpha. This means we have a 95%. So if I want to do a confidence interval for this to get 95%, I want to be between 2 pieces. So let's see what our choices are for that. So let's go to the options. We change it to the confidence level of 95%. Because to me, if I'm confident between these two of 95%, it's the same thing as using the 0.05 level. All right, so we are confident between a lower limit. Well, let's look at the Z. I'm going to look at the picture too. So they say our lower limit's between 0.5593 and negative 0.1747. So this is our 95% confidence interval, but it's showing that our critical Z is away from that, right? So let me try to show you what I'm trying to say. So if I just go to calculator, and I just want the normal graph. Okay. Sorry, it got all fat. Move this. Okay, so remember previously, right? Previously, we're at the 0.05 level, right? So we just had to be less than this 0.05. That's why the critical is negative 1.644. Do you see that? That's how they got this value. And our test statistic was what? -3. It was all the way over here. Okay. Now we want a between, right? We kind of want a confidence interval of being what? Sweet. So if I'm at 95% right here, this is showing that we have to be what? Everything less than this one. Because we're still below it. So that's why it says 1.9559. Now, if I push this to 0.975, we're at 2, right? We're going to be at 2. And I think that's what we have to do because we're splitting it in half because we're only taking it from one of them. Our left limit is 0.05. Now our left limit is, let's go back to this one. Okay, that's our critical Z. If I make it 0.975, our critical Z is this. But we only want to the left, right? Because we have to be confident. So I'm pretty sure that this is where we get this value from. I don't know. Why don't we hold off on this for number 2? I'm sure I'll do another confidence interval. We'll see the difference because I can check it later. So we'll hold off on 2. I'm pretty sure this is the right answer. And the question saying, what feature of the confidence interval leads to the same conclusion as exercise 1? What feature? Okay. The feature that's the same. Well, our critical Z is not the same. What feature? I believe that the lower limit and the upper limit should give us the same value. So we should be falling outside of the lower and the upper limit, this 0.5 and this 0.71. Since this falls outside of that, we know it's significant. That's what I think it is. But we'll go back to 2 after I do one where we can look up the answer. All right, let's look at 3. Maybe it's got a confidence interval for us. Listed below are the actual temperatures along with the forecast 5 days earlier. Use a 0.05 significant to test the difference between actual temperatures and the temperature forecast 5 days earlier with a mean of 0 degrees. So actual temperatures along with the forecast. So these might think that they're the same. You might think it's dependent, but this is independent. Because they say temperatures, but it's not the same person getting it. One's from the author who's actually getting it, and one's from like the news place, so they're different. So I actually typed these in already for us, so I didn't have to like waste my time doing it here because I was like, oh, there's a table, so I dropped these in for us already. So the first thing I have to do is this is a t-test, t-stat, and now we have to sample with data. We have data for the first time. So we can select the actual temperature for the first, or we can build it. We can select a forecast. We have to pull the variances. And are they saying it's the same or different? Okay, so we just want to say that is it 0. We don't know if it's bigger or less than. This is a two-tailed test. So our first one, mean 1 is equal to mean 2, which is equal to 0. There's no difference between them. And our alternative is just mean 1 in minus mean 2 is just not equal to 0. That's it. Now let's show the critical value. Let's see if we got this right. All right, so our t-stat here is negative 0.2347. Our critical value, when we're testing it against, is 2.100. Notice that it's always higher when you're doing two-tailed, and the p-value is 0.8171. What does this mean? So our t-statistics over here, because we just want to make sure they're not equal. So our critical value is here at the 2.1, but we're over here. We're in the mess. So our t-stat is not bigger than what we need. We wanted to be here, but we're not there. So this is not significant. So we fail to reject the null. So let's see if that's right. And a good way to test this, we could go to calculators. We could go to the T1. Notice it's different than the Z1 we had before. Our degrees of freedom is 18 because we have 20, but there are two groups, so that's why we subtract 2. That's where the 18 comes from. And we're testing this at 0.5. But since it's what's it called? Sorry. So they got 2.1. I believe it's because it's two-tailed. We got to double that. Yeah, sweet. So because this is two-tailed, like normally it'd be like 95%, right? Boom. But because they've got two-tailed, we have to take this and we're kind of like adding more to it. So this 5% that's left over is now, you can think about it as like the alpha is divided by 2. So that's why it's 2.5%. That's why instead of 95, when we put it in the computer, it's going to be 97.5%. I believe that happens because it's two tails. Let's see if this changes for one tail. I always want to see. See, look, our critical value is down to this value. And is that the 0.95? Yeah, sweet. So that's why. I just want to double check things. Obviously, it's a new program for me too. So because it's two-tailed, we have to double that space. If it was a one-tailed test, our critical would be 1.734. But because we have two-tailed, it's still not significant, just so you know, it was one-tailed. But because we're two-tailed, it makes it the 2.1, which is 0.975. All right, let me check it, make sure this is right before you try 4. Says the test statistic, the answer for number. Oh, they have the answer for two in the back. Sweet, because it's a review. Let me wait on it though. All right, so our test statistic is negative 0.20. I sorry, it's negative 0.262. We got negative 0.234. We got negative 0.234. They got a p-value of 0.7995. And we got a p, yeah, this is all for us. So I might have typed it in wrong. So let's try this again. I made a little bit of an error. All right, let's actually just jump into number two. Let's see what the problem was for two. I didn't know they had the answers for all of them for the review. I thought it was only odd. So let's look at two. Two says it's a 90% confidence interval. Okay, so this means we're going from it's 90% here. We have to say it. All right, so we have the P1 minus the P2. The confidence intervals does not include zero, so it appears that a significant difference between the two proportions exists. And so they got the value negative 0.528 and negative 0.206. Okay, let's see. So let's go back to number two. So it says 0.05, 95% sure. I don't know why it doesn't tell us to use 90%. All right. So, oh yeah, I remember it's from that table. So if we have a 0.05 alpha level, we're always using a 90% confidence interval. It's from a table. I hate when it's just because it's from a table, but you can look it up. It's definitely in the back of the book. Believe this one was the table for, I believe it's for binomial probabilities. Or it's the one for z-scores. Let's find it. I remember seeing it. All right, well, it's not this one. It's at the very bottom. Yeah, here we go. Oh my God, sorry. Now let's go with this one. Okay, is it for the t critical values? All right, so we need the table. This is how we find it by hand. It's 1 minus alpha, so 90, if it's 5%, it'd be 90%. But why are we going 90%? Oh, I was right. Most confidence levels at 0.10 should be 90%, and 0.05 should be 95, and a 0.01 should be 99. So I guess the back of the book made a mistake because this one says it should be 95% like I had it. Am I going to argue with it? No. And this is if it's two-tailed. If we had a two-tailed, just like I said before, the critical value for the confidence interval. That's why the last one was like we had to make it to 0.975. Oh, oh, but these if they're just halved. Finding the critical value for a 95% confidence interval is 0.05, 1.6. But for 90%, it's this 1.645 critical value. 90% is for, okay, so I know why they did 90%. It's because the critical value matches it. That's why in the back of the book they use 90%, because for our first one, stat, proportion stat, to sample with summary. When we do, I'll just do the first way first. It's less than this. The values were, I believe, oh wait, I have it written down. It was 12 and what? Well, look, it says that the critical value is this negative 1.644. That's why they use the 10%. That's why they use the 10%. Because you could see right here on this little table. So I would have normally done this, but they're going with the critical value. Here, let me just copy this table and just put it right. I don't want to create a flashcard. I just want to copy it. So we have this to play with. Nope, that's somebody's email that I was trying to help. Try one more time. Well, it doesn't want to be my friend, so I'm just going to screenshot it. Nice. So now I have this to play with whenever I need it. All right, let's go back to the problems. So we're in chapter 9, the review. Where is it? Review exercises. Here we go. So for the first one, it was 12, 46, 27, 43. 12 people spent for the $46. It was 27 people spent the quarters for the 43 quarters. Right? Yeah. All right. So let's show the critical value. And we think it's going to be less because more people are going to spend the quarters. Now look, it gives us this critical value here of this negative 1.644. So even though we tested this at a 0.05, right? We tested at 0.05. They're saying when you have a critical value, you should be using this 90% confidence interval. That's why. That's why they use 90%. So ready? We're going to go to options, edit. I'm going to change this to the confidence interval, but we're going to make it 90%. I'm going to click compute. All right, so this is our answer. So for 90%, this is how they got the lower limit of the negative 0.52 and the upper limit of the negative 0.20. Now, because the standard critical is like not in this, it's not in these limits, excuse me. I think that is why it gives us the same answer for these. So that's the reason. I think that this value is so small that we're going to fall outside of it and our critical value falls outside of it. So that's why I think that. All right. So let me try 3 again. So I did 1 and 2. That's why it's 90%, because our critical value was this 1.644. So we're using the same critical value because that's 1 for 90%. That makes sense. All right, let's go to 3. So I messed up 3. So I might as well, because I got different answers. Might as well just see if I typed it in wrong, because that happens, right? I'm human. So let's try this thing again. All right, so let's start with 3 from the beginning. And let's make it work. Let's get the answer that's in the back of the book, right? It's like the beauty of math. So our actual temperature is 80, 77, 81, 85, 73, 73, 80, 72, 83, 81. All right, so we got 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and the bottom is 80, 80, 79, 80, 79, 82, 76, 73, 77, 83. Cool. So this is our actual temperature. This is our temperature forecast. So let's go to data. We're definitely doing a t-test here. So statistics, t-test. We got a 2-sample with data. So we're taking the values in actual temperature and the values in the temperature forecast. We're pulling the variances. We're saying that this has got to be not equal, and we're doing a two-tail test. That makes sense. And let's show the critical value. All right, let's see what it says. All right, so my critical value is still this 2.10092. They have a different critical value. They have 2.262. They have a different critical value than me. All right, so the first one is mean 1 minus mean 2 does not equal 0. And this is the t statistic they got was negative 0.206, negative 0.262. Let's try without pulling the variances. Let's see what happens. Now it's negative 0.262. And this t-stat is negative 0.234. It's still off. This is the difference between two means. All right, well, that's everything. We might as well look at one. Construct a confidence interval with the plane views for exercise 3. To me, there's nothing wrong here. But it's not just a two-sample hypothesis test because they say that we're using the means, so that's right. All right, so since I'm getting the wrong answer, I could do this by hand because there's not that many numbers. And let's do it by hand. Let's see if we get the back of the book, or there's probably some difference in the options that we're missing. The two-sample hypothesis t-test, that's what it is. There's no way they did a, do you think they did a paired sample test? But it's not the same thing. I doubt it's a paired sample test. I might as well try it just to see. All right, so this one, they got the t statistic is negative 0.262, negative 0.262. They did think it was paired. I don't think it's paired, but I'll explain why they picked paired. And their critical was 2.262. Yeah, okay, so this is what they did. They thought it was a paired sample t-test, which I definitely disagree with, okay? Now, this is the answer. However, to me, a paired sample is like the exact same person being tested like before treatment, after treatment. They think this is a paired sample because it's the same day. were using the exact same day, and one was the actual temperature and one was the temperature forecasted. That is why they thought it was a paired sample t-test. Personally, to me, I think they're coming for two completely separate sources. However, I can see there from their reasoning that it is both on the same day. This was a Monday. It was supposed to be 80 degrees. It was 80 degrees. The next day is a Tuesday. It was supposed to be 80 degrees, but it was 77 degrees. That's why they made a paired sample t-test. But me personally, I went dependent. Um, yeah, I'm okay with that. But that's how they got that answer. So let's write it in. So this is the answer number three. So three, the hypothesis is that there is no difference in the means, and our alternative hypothesis is that there is a difference in the mean that's not equal to zero. Our t statistic here is negative 0.262, and our critical value is going to be 2.262. Not significant. What does that mean? So we're here. We're at this 2.262, and it's basically because it's just not equal to zero. We've got like kind of like a two-tailed idea happening. This is a two-tailed test. Just makes it that everything a little bit different. So that's and our p-value though. I mean our t statistics is here at the negative 0.26. So we're not in this region, right? We're not in that region. You could always look at the t statistic to just get that value. So right now we have, I believe it was 0.05. Yeah, they use 0.05, right? So here's our 0.05. That's not the right one, right? Um, so it should be 0.95 in the other direction. However, because it's double, why do we have to double this? Or why do we have to make this bigger? We have to make this bigger because, oh, sorry, my degrees of freedom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Degrees of freedom, since I have 10, it's always one less. So this is going to be 9. But because I have two groups, right, it's going to be 8. I guess it's 9 because it's the same group twice. Yeah, cool. So the two-tailed test makes this a 0.975, excuse me. And now we have this 2.26 because the degrees of freedom is how many groups we have. Consider they're saying that each one of these are the days. So we only have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday. Um, they all account for the same exact day. That's why there's only one degree of freedom. That's how they got this critical value, the 2.262. I know that's a lot. I know it's confusing, but let's just keep on going. Let's go to number 4. Hopefully it doesn't scare us too much. So in this case, it's bigger than 0.05. This value does not exceed this value, right? We have to be here, but we're here, right? We're just here at this negative bit, but we want to be here. So for this one, we're going to fail to reject the null. I'm just glad I got all the right answers. So we're going to fail to reject the null for number 3. And what else are we going to do? We're just going to put in every piece of this. So T stat negative 0.261, it's negative 0.262, critical value 2.26. Obviously does not exceed. We fail to reject the null. There's no difference between the temperature predicted and the temperature of the day. All right, let's see what 4 has in store for us. All right, so number 4 says, oops, sorry. Number 4 says, construct a confidence interval that can be used to test the claim in exercise 3. So this is our critical T, right? This is our critical T value, this 2.262. Based on these results, it's appear that the forecasters are doing a good job. So for number 4, we just basically need to figure out our confidence interval. This says 2.262. It's basically going to be the same thing. I'm going to be using, for 2.262, we should be using 0.975. However, in this case, they're using a 95% confidence interval. So to be honest, I'm not really sure whether you're using this confidence interval for this one and the other one for the other one. I would assume because it's 2.2 for our critical T and 2.2 is at 9.975% that we would be using this. Oh, but it's 2, so this is essentially 9.5. Okay, that's why. Sorry, it's confusing to me too. So this is still a 95% confidence interval for what? This test, this critical T. The only reason why we have 0.975 is because it's two-tailed. So to get our confidence interval, all we have to do is change this. It's not 0.90, it's going to be 0.95 because that's what essentially matches to this T value. Okay, I think that's all we need. Sweet. Sorry. So this is how number 4 is supposed to make sense. All right, so number 4. We use our 95% confidence interval. See, 9 degrees of freedom. I'm glad I got that right. Our critical T is still going to be this 2.262. That's why we still have to use 95% because it keeps the critical T the same every time. So this means we're 95% sure it's going to be between negative 3.858 and 3.05. This is where it should fall between. Our value is here. We have a 2.262. So what does this actually mean for us, right? We're falling between this. We're falling between this. It just means that because they're falling between this range, they're not bad. They're not bad at their job. If they were over here, they're over here, they'd be too high, but they're here, which means we are 95% confident that the forecasters are within, are able to predict the weather from 5 days before. That's why that's the right answer. We're falling between it. If it was here, it'd be different. We're too high. If it's here, it'd be different. We'd be too low. All right, let's keep going. What does the next one say? I think we're good to go now. I might as well just put this right there. Yeah, okay. So, okay, this is the last one for this group. Here's number 5. All right. Among 198 smokers, so for number 5, our N is 198. 51 were no longer smoking after 6 months. So this means 51 quit. And in 6 months, among 198 smokers, 51 were no longer smoking. 199 who went, oh, so there's different programs. Okay, so now I have 199 people who did it. So this is sustained care. So ST care. This is standard care. So SD care, standard and sustained. Okay. So here we have 30 who quit. Journal of American Medical. We did this one before. This is a really good journal. We want to use a 0.01 significance to claim that the rate of success response is greater than this program. All right, so for number 5, I believe we're doing number 5. Okay, so number 5, we don't have means here. So we just have to do the probability ones. So that means we're going to be using z-scores. So we should be good to go. So we're basically just going to be using this. It's like the proportion one. So for number 5, we're using proportions. So our null hypothesis is going to be the probability of sustained is going to be equal to the probability of standard. And our alternative hypothesis, they want to claim that the rate is greater with sustained. So sustained is greater than standard. So this is my null and alternative hypothesis. We have the values, right? 198 to 51, 199 to 30. So all I'm going to do is go to stat, proportion, 2 samples with summary. So the first one was 51 out of 198. The second one was 30 out of 199. They probably had 200 people in each, and a couple people dropped out. And it's not that it's not equal. We're claiming that 1 is going to be greater. More people dropped out in 1 than 2. And we have to use our significance at what level? 0.01. So that's what it says. So let's compute that. All right. Is it significant? Yeah, it is. 0.0041. So it is significant, which is great for us. It's really good. Since we have something significant, we are good to go. So test the claim it is significant. If you want to look at it on the little table, like I keep showing you, we can pull up the calculator for normal. And we want to make this 99%. Mean is 0, standard deviation is 1. We just want to make this 99%. Do you see how this is 2.326? 2.326. That's how you get that critical Z. Our Z is bigger. So if we look at the critical value, we see we're bigger. If you look at the P, it's less than 0.01. That's what we need. So either way you want to write 5. Sorry. So either way you want to write 5. Either way, we're going to want to write 5. You can tell that it's going to be significantly different. So 5, either it's we reject the null, which is what we want to do. You could either use critical value, right? We exceed the critical value. You could use those numbers. Or we could say that the p-value is less than 0.01. Use whatever way you'd like for this. But either way, we know it's significant. All right, so that was 1 through 4, 5, and we get to do number 9. Whistleblower waist circumferences. Use a 0.05. Of randomly Army male personnel from 1988 of differently randomly selected. Okay, sweet. So we at least get to do one that has what for number 9? That has that is not a dependent, it's an independent sample t-test. So here we go. This is not what we want. This is not what we want. This is not what we want. Okay. So basically to do this one, all you have to do is go to stats, t-stats, 2 samples with data. But I have to write the data. All right, so 1988, 2012. So 808, 852, 729, 841. You'll see that now the degrees of freedom will be two less instead of one less. 825, 903, 874, 935. Okay, so that's 1988. Here's the 2012. 787, 938, 933, 986, 946, 748, 934, and 802. So before we do this, we go to T-stats and we just want to say test the claim difference is the plan with a mean of 0. There is no change. Okay. What is seriously wrong with this question? Well, you're using different guys. I don't know. I was going to do the problem. They just want to know what's seriously wrong. They're not matched in a meaningful way. Okay, whatever. I don't care. That's what they think is wrong with it. I'm going to test it though. So first, let's go to the calculator, the T-stat for this. Our degrees of freedom should be 8. And we want to do this at 0.05. But because it's a two-tailed test, it should be 0.975 if we go that way. So this should be our critical value. We should get a 2.306 for our critical value. But let's see what I got. Let's do the whole thing and everything else. So T-stat to sample with data 1988, 2012. They just want it different. We're talking critical value at 0.05. Let's see what they get. Their T statistic. Their critical is 2.169. That's strange. Oh, I didn't pull the variance because the degrees of freedom are off. Sorry about that. It says our critical is 2.144. Their degrees of freedom is 14, which I don't like at all. Okay. Well, that's how you could get it. We have to double this because it's 5%, but it's two-tailed. That's why that makes this the 2.144. But let's see what the book got. Oh, they're still doing it the other way. The book is still treating them like the same person being matched over and over again, but these are different people. So that's the problem with the book. I guess the book didn't teach you how to do this one yet. That's why it keeps using matched every time. But these aren't matched. These are like dependent, in my opinion. So this is what the book did, like a fool. So they made them paired for some crazy reason. But you can't pair these people. It's not the same person over and over again. Okay. One, two, three, four, five, six, seven, eight. Yep, they just treated it like it was what? 4 people. That's how they got their values. Yeah. Yep, 2.364. Is that what the book has? Yep. Okay, so this is the answer that the book has. They're matching these people. I consider these completely separate, but they match them. They're pairing each person up for some reason. That's what's seriously wrong with the question. All right, I guess I could look at 4, 6, and 7. Or I guess you guys could do those 3 if you want, unless it looks interesting. The IQ scores of twins, the data are pairs from 10 different families. pose a key question, identify the procedure, analyze the data. All right, I guess I could do number 4 for you because it doesn't look hard. And do they have the answers for these? Yeah, okay. To me, it's just what we just did. Is there a difference in these kids, right? So the null hypothesis would be that there's no difference. So it's a two-tailed test. So the alternative hypothesis would be there are two different tests. These are definitely paired samples. To me, they're a total match. So all I have to do, I'll just do the first one. So we'll do firstborn and secondborn. And you'll just have to do the rest yourself. So 96, 87, 101, 103, 127, 101, 93, 94, 97, 113. And our secondborn is 89, 87, 103, 96, 126, 96, 88, 85, 114, 124. So the null hypothesis would be that the firstborn is the same as the secondborn intelligence. The alternative would be there's some difference. So it's two-tailed. We're going to use a 0.05 significance level. But basically, this is definitely a paired set of data. So that's the firstborn. That's the secondborn. We're just going to say that there's some difference. And we are going to show the critical value. Oops. Sorry about that. Cool. So there's no significant difference. How they get the critical value? Well, to get the critical value, it's two-tailed, so it's basically we can go to stat calculator normal. And so we know it's going to be 0.975. Oh, sorry, it's not normal, it's a t-test. So we got to go to calculator, t-test. Our degrees of freedom is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 9. And we have 0.975 because it's two-tailed instead of one-tailed. And so we have a critical value of 2.26. There it is, 2.26. But ours was 1.1 something, it didn't exceed it, or you can see that this is not less than 0.05, not significant. So there's no significant difference between the IQs of the firstborn and the secondborn childs. All right, that one I explained really well. For 6, an experimental tested eyewitness after a non-stressful of a cooperative and 1 week after the stressful of an uncooperative and belligerent suspect. The numbers of details recall 1 week after the incident recorded. And is it the same person? Of police, eyewitness memory of police 1 week after a non-stressful interrogation of a cooperative subject. All right, so to me, this is again, it's a match. This is matched, but we have because it's the same guys, it's the same person, just doing it twice. Doesn't say they're separate groups, but the only difference for this one is that these paired samples, sorry, is that I guess we could do it with the summary, right? I guess it's just a sample with summary because we don't have the rest of it. So I guess now they're letting you use the other formula. I don't know why, but am I gonna argue with it? No. So the sample mean for the first one is 53.3. The sample standard deviation is 11.6, and we got 40 guys. All right, the sample mean for this one's 45.4. The standard deviation is more deviations, more range, and the sample size is 40. We always have the polar variances, and they want to know experiment test the eyewitness memory of police. Test the eyewitness memory of police. So it's the same cops, and I'm assuming that it's going to be better. So this can be a positive number when it's not stressful. So that's what I'm going with. Let's use a critical value of 0.05 and let's compute this thing. All right, we have it's one-tailed, that's why it's right here for it's the 1.66 for the T. It is significant. It's significant difference. All right, let's look at the book. Let's make sure it's the same. Reject the null. They got 0.0029. We got 0.0033. Their T value was 2.83. Our T value was 2.75. The test is this, which is 2.34. And they use the critical value. All right, well, all of these are a little different. So let's see if I did something different. So I think it is because they still want this to be paired, but I don't have data for it being paired. All right, let's see. Let's see what 9 has in store for us, just for this one. Let's see whatever formula they give you for 9. Two independent samples, but that's not equal. It's the formula I did last time. But I believe this one, they want it to be a matched pair for some reason for number 6. No, it's not. It's not a matched pair. So I think I just have to use the formula. All right, I'm gonna use this formula to get the T statistics. Sorry, my allergies are going crazy. Let's do it. Okay, so I'm gonna pull out Excel and use this to be my friend. Because I know the formula, I might as well just make it happen. So T is mean 1 minus mean 2. All right, here's this cop situation. All right, so mean 1 is 53, so got non-stressful. So we got 53.3, that's the mean. Got our standard deviation at 11.6. Stressful, we have a mean of, and we have the M's point for each. Cool. All right, so this is what we have. This is what we have for these, okay? So all I have to do is use the formula to make my friend. So the first one, this is the numerator. We're doing the t-statistic. We'll do the numerator first. So the numerator is mean one. Sorry. Equals parentheses. But I don't have this sample mean. Oh, this is often assumed to be 0. Okay, we're going to assume that's to be 0. Perfect. So mean 1 minus mean 2. All right, and now our denominator is going to be equals the square root of double parenthesis. So I need this one. Sorry, I need 2 first. Yeah, sorry, the first one divided by 40 plus the second one divided by 40. We found the typo. Oh yeah, I forgot the ends. Cool. So this is just going to be the numerator divided by the denominator. So I got a t-score of 9.953 for this one. Let's see what the book got. They got a t-statistic of 2.843. That's a problem. Oh, because these are the variants, so I have to square both of them. So that's not a big deal because this is the variance, not that. So all I have to do is take this number and times it by itself, and take this number and times it by itself. Nice. So 2.795, and they got 2.843. All right, well, I got 2.795 for mine. And what did this get? Yeah, sweet. 2.795. So when we do this paired, should be it should be that value, right? We have the t-statistic. I got the 2.795, but the back of the book got something different. So I might as well keep trying to figure out a way. So they're doing a 2-sample t-test. I did a 2-sample t-test. I got a t-statistic of 2.795 and a critical value of 1.66. It is significant. They got a 0.0029 p-value. I don't know where the difference is coming from. Uh, is this because I pulled the variances? Try without pulling the variances. Their p-value is 0.0033. No, 0.0029. I still am getting the same value every time. So I think this is the answer. The back of the book has something different, but we're both rejecting the null, which is great, right? We're both rejecting that null hypothesis, which is great. So what would I recommend? I'd recommend trying this one yourself. I don't know why. I think it's when we don't have the data, some things are a little bit different, but we might as well see whatever this last one is, just so we could look at one more. As long as I'm getting it by hand the same way that the computer gets it, I could care less about the back of the book. I think there's one more in the cumulative review. All right. So I did four, not correctly. Oh no, I did four correctly. I did six not correctly. And here's seven. Alcohol, drug use, total population, road accidents, tobacco, war, murder. Pose a question, use data. Okay, so this is the probability one. We have to see if there's a difference between the two. I'll let you try seven yourself. Remember the answers to these in the back of the book. I hope this was helpful on just reach out to me if you have questions about it. Sorry the police one I couldn't get the right answer to, but as long as we're both saying it's not significant. I think the real big takeaway from this is like really have to think about, is this paired? Are they fully matched? Are they paired up? Are they matched? Or are they fully independent samples like men and women? So really try to keep that in mind when you're doing it, and good luck.